Good morning to all. Now we will discuss on session 9 from the first unit, that is laws of motion, for the first semester students of Gulbarga University, Kalburgi under CBCS scheme. The title of the program is Mechanics. Here we are going to understand the Newtonian mechanics, frames of references, relativity and dynamics of particles of system. Let us have recap of the previous class. In the previous session, that is session 8, we have discussed about the rotating frame of reference, in which we have come to know about the Coriolis acceleration and the force. And the objective of this session is to learn about the center of mass and the center of mass frame of reference. The outcome of this session is understanding the center of mass and the center of mass frame of reference. To understand about these center of mass and the center of mass frame of reference, we should know about the frames of references, important concepts, some terms, Newton's laws of motion and its limitations, inertial frame of reference, some of the concepts of absolute space, time and motion, Galilean transformation equations for both inertial and non-inertial frame of reference, and also about the rotating frame of reference, in that the Coriolis acceleration and the force. Now the introduction about this center of mass. The concept of center of mass was first introduced by the ancient Greek mathematician. He was a physicist as well as an engineer named Archimedes. So Archimedes was the first person to give the concept of center of mass. Archimedes showed that the torque which is exerted on a lever by weights resting at various points along the lever is the same as what it would be if all of the weights were moved to a single point, their center of mass. In the Middle Ages, theories on the center of mass were further developed by other scientists also. So now we'll come to know what is center of mass. The center of mass is the point where all of the mass of the object is concentrated. The center of mass is a function only of the positions and masses of the particles that compose a system. This is also oftenly called as the center of gravity. But this is not always true. This is only true in a system where the gravitational forces are uniform. Suppose if you want to find out the center of mass for two particles. So how to find that? The center of mass of a two particle system lies on the line connecting the two particles. The center of mass is closer to the more massive object. So if you consider two particles of different masses, and if you are finding the center of mass for these two particles, always it lies closer to the more massive object. If the center of mass is a point within the object, then the object can be balanced at that point. Suppose if you want to find out the center of mass for a rectangle, then how do you find? The center of mass of a rectangle is at the intersection of the two diagonals. You need to draw the two diagonals for the rectangle, and these two diagonals are going to intersect, and the point where they are going to intersect will be the center of mass for that rectangle. If a rigid body is projected through the air, its center of mass will follow a natural parabolic arc. Then there are different methods for finding the center of mass. So in physics, the center of momentum frame, which is also called zero momentum frame or center of mass frame of a system, is the unique inertial frame in which the total momentum of the system vanishes. So here in this kind of frame, whatever the momentum is there, that total momentum is going to vanish. The center of momentum of a system is not a location but a collection of relative momenta, relative velocities. Thus, the center of momentum means center of momentum frame and is a short form of this phrase. A special case of the center of momentum frame is the center of mass frame. So, center of mass frame as well as the center of momentum frame are same. It is an inertial frame. So, here what happens? In this kind of frame, center of mass remains at the origin. Suppose at the origin you have the center of mass, then that frame of reference you call it as the center of momentum frame or center of mass frame. In all center of mass frames, the center of mass is at rest, but it is not necessarily at the origin of the coordinate system. It may be anywhere, but it must be at rest, need not to be at origin only. In special relativity, the center of mass frame is necessarily unique only when the system is isolated. Let us summarize about this session now. Center of mass of a body or a system of particles is defined as a point. It is a point first of all at which whole of the mass of the body or all the masses of a system of particles appear to be concentrated. When we are studying the dynamics of the motion of the system of particle as a whole, then we need not bother about the dynamics of individual particles of the system, but only we should focus on the dynamics of a unique point corresponding to that system. So instead of considering all the particles, even we can study about the center of mass also. Motion of this unique point is identical to the motion of a single particle whose mass is equal to the sum of all individual particles of the system, and the resultant of all the forces exerted on all the particles of the system by surrounding bodies. This point is called the center of mass of the system of particles. The concept of center of mass, it is useful in analyzing the complicated motion of the system of objects, particularly when two and more objects collide or an object explodes into fragments. So, the center of mass is a position. It is defined relative to an object or system of objects. It is the average position of all the parts of the system. For simple rigid bodies with uniform density, the center of mass is located at the centroid. So these are total linear momentum of many particle system is zero in center of mass frame of reference. That is, as we all know, the linear momentum is the product of mass and velocity, and in the case of center of mass frame of reference, its velocity vcm, that is velocity at the center of mass is zero, and since this velocity is 0, p is equal to mv, v is 0, so obviously p will also be 0. Therefore, this reference frame is also known as zero momentum reference frames. And since in absence of any external force, the center of mass of any system moves with constant velocity in inertial frame of reference, therefore, for many particle system, this C frame of reference or center of mass frame of reference is an inertial frame of reference. Similarly, the reference frames connected to laboratory are known as laboratory frame of reference. Now we will solve some of the questions. Question number 1. Point where force causes system to move without a rotation is option A, center of mass. Option B, midpoint of body. C, edge of the body. D, none of the above. So the point where force causes system to move without rotation is which point? The center of mass. It is a point where force causes the system to move without rotation. Hence the answer for this question is A, center of mass. Question number 2. The center of mass of a system of two particles is option A, on the line joining them and midway between them. Option B, on the line joining them at a point whose distance from each particle is proportional to the square of the mass of that particle. Option C, on the line joining them at a point whose distance from each particle is inversely proportional to the mass of that particle. And option D is none. Here the answer for the question number 2, that is the center of mass of a system of two particles, is on the line joining them at a point whose distance from each particle is inversely proportional to the mass of that particle. Hence option C is the correct one for this question. Now the third question. A body falling vertically downwards under gravity breaks into two unequal parts of unequal masses. The center of mass of the two parts taken together shifts horizontally towards option A, lighter piece. Option B, heavier piece. Option C, depends on the vertical velocity at the time of braking. And option D, does not shift horizontally. So here option D is the correct answer for this. It is not going to shift horizontally. Question number 4. The center of mass of a system of particles does not depend on. So on what the center of mass of a system of particles will not depend? Option A, masses of the particles. Option B, forces acting on the particles. Option C, position of the particles. Option D, relative distances between the particles. So here we know that the center of mass of a system of particles does not depend upon the forces acting on the particles. Hence answer B is the correct answer for this question. And these are some of the references. You can go through that. Thank you.